So this is a video that's going to discuss a radically important measure within the world of statistics, and this is a series of measurements related to dispersion. So what I'm going to do in this video is try to walk you through from a real high level the development of different measures of dispersion and how we got there. The author Alexander Holmes is famous for saying that this notion of understanding the number of standard deviations as a measure away from the mean that we are is a fundamentally important part of any statistical theory, and he's absolutely 100% correct. I could go back to personal experience within engineering and finance and in related fields and explain to quantify the amount of dispersion or variation that exists is a fundamental concept within many fields. I'm not going to go off on that tangent, but in this video my attempt is to just kind of walk you through some of the equations and the development of them, some common equations for dispersion. Now, if we look at kind of one of the most simplistic versions or ways that we can figure out the amount of variation that exists in a set of data is we can calculate the range. The range is simply the highest minus the lowest, the highest value minus the lowest value. We can all understand right now, we're going to basically eliminate this. There are some quality applications for that number on the bottom that have been built upon a lot of study. But in general, I'd say, if I could summarize that, it's the least democratic way to look at dispersion because we only have those two values that are going to count the highest and the lowest. So I think, we can all agree that that's a pretty lousy measure if we want to try to figure out this dispersion or the amount of spread that we see in a set of data. What we could do, and one of the problems that we're going to have is if we go in, one of the properties of the mean is if we total up all the values x minus the mean, all right, that total is always going to come out to 0. This is one of the properties of the mean. We can illustrate that really quickly. If we go in and we look at, imagine we have a set of values, x is 1, 2, 3. So we have 3 different data points. We total these up, of course, we get 6. Divide by how many there are, we get a mean equal to 2. If I subtract that mean from each one of these values, right, I'm just going to represent this column, the x bar minus the mean. We've got, of course, -1, 0, +1. That total for the distances away that all of these values are from the mean is always going to total up to 0. The arithmetic mean is the mathematical center of our data. And so if all we're doing is looking at how far apart different data points are, they always have to total up to 0. As a way that we could avoid doing that, we could calculate what's called a mean deviation or a mean average deviation. The mean deviation or the mean average deviation is the total of the absolute value of x minus the mean divided by the number of observations. So this is an overly simplistic set of data, so we'll use a slightly different set of data for this one. If I went through and I used the following set of values of x, 20, 40, 50, 60, and 80. All right, and the first thing I've got to do in looking through this formula is I'm going to have to find my mean. If I total up these values, of course, I have 100, 200, 250. Divide by how many there are. It gets us to a population mean of 50. Right? So if I subtract out this population mean from each one of these values, we subtract out the 50 from each one. This column over here is going to represent the x minus the mean, just like we did before with a little different set of data. So we've got what, -30, -10, 0, +10, and +30. Now we'd see the exact same condition here. If we totaled these up, we're going to end up with 0, right? Because again, this mean is the mathematical center of the data. One way we could avoid that would be to do the absolute value, right? So if we go in and we say, what's the absolute value of -30? Of course, we've got +30, +10, 0, +10, and then +30. So one way to avoid kind of this offsetting from this property of the mean being in the center of the data is to do an absolute value. With our equation, then we're going to total those up. We got 30, 40, 50. We've got 80 here, right? And then if I take the 80 and divide by my number of observations, which of course is still 5, it tells us that our mean average deviation is equal to, 16. All right. Now, we don't like that measure as much, this mean average deviation, but what we can do is we can then develop another equation. We can go in and calculate what's called a variance. And we can say now, instead of finding the absolute value, we can go x minus the mean squared divided by n. So this is going to represent our population variance. So instead of doing kind of this absolute value stuff, if you will, down here, what we can do now is say we're going to take this x minus the mean, this deviation away from all of these individual deviations away from the mean right here, and we can square them. And of course, when we square a negative number, we get a positive number. So 30 times 30, of course, is 900. Negative 10 times negative 10 is positive 100, just like negative 30 times negative 30, positive 900, positive 100, of course, 0, positive 100, and positive 900. All right, so now we've squared all of these values over here. Now we can add these up. If we total these up, we've got 2,000. 2,000 divided by my number of observations, 5, tells us that our population variance now, our population variance is equal to 400. 400. All right. We can take this progression of equations one step further. And now I'm doing this all for a population. I will do a very quick video just lining up the differences between how we handled these measures of dispersion with the variance and the standard deviation with a sample and not just a population. But we can extend this out and simplify this equation here even more. If we take the square root of each side of this equation, we're going to end up with sigma on this side and the square root of sum of all values x minus my mean squared divided by my number of observations. Now, one important takeaway is we do not need to calculate the population standard deviation. We do not need to recalculate the population variance. As you can see mathematically here, we have to pass through the population variance to get to the population standard deviation. Now that I've done this work, if I want to calculate the population standard deviation, I simply take the square root of my variance, which in this case is 400. My square root of 400 gets me to 20, which arrives at my population standard deviation. These formulas are all linked together. In the next video, I will show you how there are just a very small, slight difference in how we handle a sample versus a population. But one thing I've found to kind of conclude this video is what I've found with a lot of statistics students that have had statistics before is they tend to treat this notion of the standard deviation or the variance as some kind of a mystery. But what we need to know is we're not going to every single time we're running into these values have to calculate them. As we go forward, much of this these values are going to be stated, but it's fundamentally important for you to understand how they're calculated. There's nothing magical or strange or really overly complex about these values once you get comfortable with these specific formulas and how they're developed.